In this problem, we have a bucket. The bucket has a variety of balls in it, 17 to be exact, 8 which are orange, 9 which are yellow. We're told that we're selecting 5 of these. Two different questions here, and they're going to be attacked considerably differently. This one wants to know the probability that you get at least 1 orange and at least 1 yellow. This one wants to know the probability that you get at least 2 orange and at least 2 yellow. And these look awfully similar, so it's surprising for people to hear then that we're going to attack these so much differently. Well, let's take a look at something here. Let's look at the possible mixes of orange and yellow balls that one could get when they choose. Quite a few different mixes. Let's examine problem number 1 first. Number 1 wants us to get at least 1 orange and at least 1 yellow. We find that there are lots of mixes that satisfy that. That one does, that one does, that one does, and that one does. 4 different mixes satisfy that criteria. How many mixes don't satisfy the criteria? That one and that one. So in essence then, we have a choice, which is, do we want to do 4 different computations, or do we only want to do 2? And the answer is 2, simply because it would be a much quicker way to go. So for problem number 1, we're going to look and take 1 minus the probability of getting 5 orange. And then we're also going to take away this thing down here, which is the probability of getting 5 yellow. All right, so how do we make this happen? We know that probability has a numerator and a denominator. The denominator is the total number of ways anything could happen, number of results in the sample space. So the bottom over here would say, out of the 17 things, we would like to choose 5. And so the denominator for both of these things would be combination 17, choose 5. All right, on the top, in this case, I need to get 5 orange. There are 8 orange available. So here we would say of the 8 available orange, I need 5. Over here, we need to get 5 yellows. So we would say out of the 9, available yellows, I need to get 5. And so I figure out the combinations, and this is my answer. Take 1 minus the probability of getting all orange, minus the probability of getting all yellow, and that leaves me with the probability of getting at least 1 of each. Now in number 2, they want us to get at least 2 orange and at least 2 yellow. Well, let's look at it again. Which of these things fit this set of criteria? Only those 2. So 2 different things do, 4 different things don't. The complement would be foolish here. Okay? You only want to do 2 math problems instead of 4. You always take the shortest path. The shortest path here is doing what the question wants. All right, so I'm going to write this out in English. We want to get either 3 orange and 2 yellow, or 2 orange and 3 yellow. That's what we're looking for. That's this and this. All right, so for the first one, getting 3 orange, you would say there are 8 orange available. We need 3, and meaning multiply. 2 of the yellows, there are 9 yellows available. We need to get 2. 3 of the 8 orange and 2 of the 9 yellow. course, this is probability, so on the bottom we have 17, choose 5. Or we're moving on to a different type of mix, so we add 2 orange, 8 available orange, choose 2. And so we multiply 3 yellows, 9 available yellows, choose 3. And that's all over combination, 17, choose 5. So this represents that mix, which works, plus that represents that mix, which works. Okay? No complement here. The complement was the longer way here. Yes, complement here. The complement was the shorter way there.